I'm serious, but like, you're still like it. No. You gotta my system to be like. Is it on the yeah. What's your class? Like so long. I've been playing
Can someone on the Zoom let me know if you can hear me?
Yeah, I can hear you.
Okay, thank you.
I want this. We'll get that. It's a large one.
Hey, how's everyone doing? Made it through the snow today. Good stuff.
Yeah, it's actually nice out now.
Nice. Okay.
Yeah.
That's good. All right. So prior to getting started, does anyone have questions about the material, the homework, anything? You're good to go. Okay. So here's the outline for this week, roughly. We will complete our sort of review of our introduction to classical computing. Just briefly to remind you again of what we had talked about last week. And then we'll introduce the complexity classes. This is useful in kind of getting to know sort of the boundaries of where classical and quantum computing might intersect or where quantum computing might be more relevant. And introduce the church. We introduced the church Turing thesis. I'll just have a few more words to say about it again today. And then, voila, we start finally in week 3, we'll actually start to talk about quantum computing. And we'll begin with the basics, qubits, talk about qubits and superposition of states of qubits. And that also goes by the name of quantum coherence. We'll talk about that maybe a little. And we'll be returning to that idea constantly, but yeah. And we'll introduce an important tool for visualizing the state of a qubit, which is called the block sphere. And probably some of you may remember or have already learned about complex numbers. That turns out to be important for quantum mechanics. And so we'll do a little review of complex numbers. In case you've never seen them, let me know. I can go into more detail and so on. But it should be fairly simple at this level for what we're going to be doing, and we'll do a few exercises maybe along the way. And then measurement and single qubit gates towards the end of this week. We'll see how far we get today. Okay, so last week we had introduced the idea of the universal Turing machine. If you remember, our basic Turing machine consists of this sort of 4 different components. And anyone, they're on here, okay? But we had the state of the quantum computer of the Turing machine, the head, which goes one by one on the tape. The tape is sort of the input to the Turing machine. And then there's a program, a list of instructions that the Turing machine goes through. And we did an example the last time. And the universal Turing machine, of course, is useful because it can simulate any other Turing machine with some overhead, which is polynomial. And we introduced the Church-Turing thesis, which said that the class of functions that are computable by the universal Turing machine is, in fact, the class of functions that we regard as being computable. in general. So if I were to like paraphrase it, sort of without being too careful, it just says that all computable functions are computable on a universal Turing machine. And of course, we saw last class that there are problems that cannot be computed. And the example that was the halting problem. And we went through the proof that the halting problem has no solution, meaning there's no algorithm to determine if a computer program for a Turing machine will halt or run forever. We also introduced after that what we mean by computational problems. So like we have been sort of circling around it, but the kind of things that we want to start thinking about now are being a little bit more precise in our definitions, which is first, that one question that we can ask is, what is a computational problem? What type of computational problems will we be looking at? And the kinds of computational problems that computer scientists have sort of thought about very deeply are what are called decision problems. That is, problems with a yes or no answer. Now, of course, it turns out like a large class of problems can simply be reformulated as a decision problem, So, we saw some examples. I'll remind you of those as well. The second question that computer scientists have worried about for a while is, how can you design an algorithm to solve a computational problem? And that's obviously beyond the scope of this class. To cover all of classical computing algorithms would take an entire semester. So, but we will introduce quantum algorithms later on in the course. And finally, the thing that probably most computer scientists would like to know and understand at that deep level is, what are the resources required to solve computational problems, classes of computational problems. So you can like sort of categorize them by sort of difficulty of the problem, right? And for understanding that, they introduced the idea of asymptotic notation. We briefly mentioned that, so I'll just summarize it. I'm not going to repeat everything I said last week, but we had the big O notation, which sets upper bounds, the worst case sort of, how long it takes for the algorithm to run as the size of the problem increases. The size of the problem typically means something like the number of bits that are in the problem, right? Like the Turing machine has set of bits which are its input. And so in that same way, we want to understand how does that time required to solve the problem scale with the number of bits. The big omega sets a lower bound on the behavior of the algorithm. So the big O, as I already said, captures the worst case behavior. Big omega sort of captures the best case behavior of that. Okay, and now we can introduce complexity classes. But before we do that, let's just say, when we talk about efficient algorithms, they typically take polynomial time. Okay, and polynomial time is big O n to the power k. Okay, so here are some examples. Again, we talked about this in the last class. And then it's inefficient if it takes more than polynomial time, i.e. super polynomial. And this includes things like exponential time, which is 2 to the n, or e to the n, even if the factor dividing n or in front of n is small. Okay. And also includes things like sub-exponential. So this function doesn't grow quite as fast as an exponential, but still grows faster than polynomial for large n. Remember, again, we are really interested in the asymptotic behavior for large n. And that's why, for example, there may be individual cases of individual problems where the scaling is, say, n to the 1,000, and that's a very large scaling for small n, right? That may be much greater than, say, e to the n divided by 1,000 for small n. But by small, I could be talking about sizes n on the order of 1 million. Okay, but even then, you can check for yourself on a computer how that scaling behavior compares for different values of n, and you will see that it up to 1 million or maybe even more, n to the 1,000 is always greater than e to the n divided by 1,000. But we'll still call it inefficient, because if I take sufficiently large n, then eventually this e, the exponential, will overpower the polynomial. Okay, so that's what we mean by asymptotic limit. Okay, now we can talk about complexity classes. Okay. So complexity classes are the big sort of distinction is P, NP, and P space. Okay. So the definition of P is the collection of all decision problems that has a Turing machine which can solve the problem in polynomial time. That is called P. Okay, all those problems fall in a set. The set is called P. Okay. And the collection of decision problems in which the solution to the problem, which we call the witness, can be verified or checked in polynomial time is NP. So all we say is that given a witness, I can check that this problem is solvable, is a solution in polynomial time. Okay. And that's called NP. The collection of decision problems which can be solved on a Turing machine using a polynomial number of working bits, that is polynomial amount of memory, but no limitation on the time. So you could go forever if you like. And that's called P space. Okay. That's it. That's all there is to it. I mean, these are just definitions, and then computer scientists spend a large, amount of their time figuring out, which problem. I mean, depending on the computer scientist, they worry about, what classes of decision problems fall in which categories. Okay. And so within NP, we can also specify two other types of problems. First of all, examples of problems believed to be in NP. I don't know that there are proofs necessarily for any of these, that they are definitely in NP, which I'll come back to in a minute. But one of the problems that will be of importance for quantum computing is the so-called factoring decision problem. Okay. This problem is believed to be in NP. And and the statement of the problem, as you can see, is that it basically checks, it basically casts the problem of finding the factors of any given number. Like if you have a large number, want to find its two prime factors, then we can cast that as this problem here. Okay. Given a composite integer m and L lesser than m, does m have a non-trivial factor less than m? So you can see we have made it into a decision problem. We can say yes or no to this problem. Similarly, another famous one is which is called, I think, the Hamiltonian cycle. That is given two graphs, networks of vertices connected by edges. You can think of almost many different types of problems, computer networks, roads, bridges, etc., etc. Those could be thought of as graphs, networks of vertices connected by edges. And we want to ask, is one graph equivalent to the other? So is there a map, a function that preserves adjacency of vertices, right? Two vertices are adjacent if there is an edge that connects them, okay? And we can ask whether there exists a function that will take one graph and convert it to another graph by preserving the adjacency of the edges, okay? And now we can define something called NP complete, okay? And NP complete in some sense can be thought of as the hardest problems that are in NP. Okay? And what this means, again, when I say it's hardest, is that any problem in NP can be reduced or simulated by this problem in polynomial time. So I can take one problem, run some algorithm to convert it into an equivalent or into this problem. Okay. And so if I can solve this problem, I can therefore solve the other problem, which is in NP. Okay. And that problem is, so these are the hardest problems in NP. They're called NP complete. Given an integer m and a graph G, does G have a subset of size m? Similarly, given a finite, this is called the subset graph or subset sum problem. Oh no, this is the subset sum problem. This is some other name, but it's a subset problem again. Right. So this one is the subset sum problem. Given a finite collection of integers and a target m, is there any subset which sums up to m? Okay. Very simple. As you can see, the formulation of these problems is they don't sound very difficult, right? maybe even intuitively you can say, oh yes, I can check, at least for small problems, we can all easily understand how to check for the answers, right? But it becomes harder and harder as the number of integers or number of, the size of the graph, et cetera, increases. Okay. Oh, that reminds me, somebody last class, I don't know who, had asked me a question and I felt like I didn't give a very good answer at the time. I went back and thought about it and I came up with the right answer, but let's see, where is, let me, right? So I think the question that was asked is, if it was for the reversible gates that we constructed. So we said we can always take A, B, and C, and then if I want to create a reversible gate, I just take the C and I XOR the output. XOR the output, and that gives me F of AB with C. And this was the general construction, if you remember, of reversible gates in the last lecture. And I think, I can't remember, somebody said, well, if right, and we need to have A and B as well. So I think somebody was asking, well, if I have A, B, and the function, why can't I simply reconstruct the original? And the idea is, it actually becomes evident as soon as you write down the truth table. Okay, so if you write down the truth table, and let me just take A, B as an example. Okay. So I have inputs A and B. I have A, B, A, B. Okay. So I have 0, 0, that maps onto this function, right? I mean, this values, right? For these three numbers. So I have 0, 1, I have 0 again, or let me put AB at the end just to make things more clear. So I have 0, 0, 0, 0, 1, 0. Okay. And then I have 1, 0, I have 1, 0, 0. Right? I have 1, 1. I have 1, 1, 1. And so the problem is that once again, we have a incomplete map. Basically, we have several other possibilities that could also map onto these same choices. So if I consider, if I write, like, for example, let's see, what about the state 0, 1, 1, right? What about that? There's nothing on this side that corresponds to it. Okay. So we run into the problem, we have 2 inputs and 3 outputs. So once again, there is like an over mapping, if you like, that exists. And so we can't go back. We can't reverse back to find the answer from the set of all possible values on the output. Okay. We are over specifying the input, so to speak. Does that make sense? I don't know who asked the question, but at least that's my sort of simple-minded explanation. Sorry, now come back to this. A problem is NP hard. This may be another word you occasionally hear about NP, is any problem in NP can be reduced to this problem in polynomial time, but the problem itself may not be in NP. Okay. Sounds weird, but yeah, there are, and one example of that is the halting problem. We know the halting problem is undecidable. So it doesn't belong in NP. Okay. But it turns out that every other problem can be reduced to every problem in NP can be reduced in some amount of time to the halting problem, right? And so the obvious then corollary is that all NP complete problems are NP hard, but not vice versa. And of course, a halting problem is kind of unique, right? It's undecidable. So maybe it should have its own category. But it doesn't even really belong in the sort of set of decision problems. But there are other examples. There are other problems. You have to go more deep into computer science to understand them. But there are other problems that can be reduced, or every problem in NP can be reduced to that problem in polynomial time. But that problem itself is not in NP. And of course, remember, the definition of NP is that the solution can be checked in polynomial time, right? And so we have to have that as a definite classification or a definite attribute of the problem. Okay. So P is clearly in NP, right? Because if I have a problem that has a solution in polynomial time, I can find the solution in polynomial time. Then I can obviously also find that the solution is correct in polynomial time. So P therefore must be in NP. Okay. And P is also obviously in NP space because it's a problem that has a finite number of bits. I mean, it can run in a finite amount of time. So even if I only have a finite number of bits, I can just keep, even if the problem itself is much bigger than what I have, I can just like keep running the same versions or different versions of the problem until I finally find the answers. So this is, and NP is also thought to be in P space, okay? Because even if the problem takes, if I can find the solution to the problem, right, and verify it in polynomial amount of time, then in P space, I have infinite amount of time. So even if I have a small amount of working memory, I can just simply, again, repeat the checking procedure. So the questions we can ask, I mean, this is sort of what computer scientists believe is a set of how these different complexity classes are organized. So, P, we think, is a subset of NP. And of course, as you know, I've told you about the NP complete problems that are also a subset of NP, right? And then there's P space, which is thought to, be bigger than either NP or P. So, and these are two important unresolved questions. That is, are there problems in NP that are not in P? So is in fact NP bigger than P? Okay. And are there problems in P space that are not in P? You can also ask that question. Both of these questions, we don't have the answer. Okay. So it's a sort of unsatisfactory situation. Okay. But if you ever solve these problems, there's $1 million waiting for you, because these are among the Clay Millennium problems in math or computer science, if you can solve them. Okay. So they're worth $1 million. So okay. Okay, any questions on all this? It's a lot of definitions, and it's not something that we'll talk about a whole lot in the rest of this course, but it's important to get this picture right now. So, I maybe went too fast. Any questions so far? Okay, now we introduce something called the strong Church-Turing thesis. Okay, I introduced the Church-Turing thesis earlier. And remember, I told you, or maybe you can answer this question, the Church-Turing thesis, do quantum computers violate the Church-Turing thesis? This is a decision problem for you. Yes or no? Do quantum computers violate the Church-Turing thesis? Anyone? How many think yes, they violate the Church-Turing thesis? Nobody. You think they violate the church Turing thesis, quantum computers?
Yes.
Okay. All right. And how many think they don't violate the church Turing thesis? Okay. A few. Rest of you, you're not in the decision problem category. You've decided to be undecidable, like the halting problem. Okay. So the idea is, remember that the church Turing thesis says any function that's computable is one that can be computed on a universal Turing machine. And so we think that quantum computers do not violate that. We think, of course, but we are fairly certain of this. Like, for example, we know quantum computers cannot be used to solve the halting problem, as an example. Okay. So the church Turing thesis, we can think of that as the weak church Turing thesis, if you like. Okay. Says that any function that's computable can be are the ones that we think can be computed on a Turing machine. What this one says is any model of computation, be it the circuit model or something else, but some other model of computation. There are many other models of computation, which you can go onto Wikipedia, Google, and look for. Okay. The circuit model is one we have seen already, right? The gates and all that stuff. And it was shown by Shannon that the circuit model can be sort of represented eventually by just a probabilistic Turing machine. Shannon, Turing, Church, etc. What do I mean by a probabilistic Turing machine? It sort of extends the class of Turing machines. Okay. So, but it just says that, okay, by probabilistic Turing machine with at most polynomial increase in the number of operands, which, as we know, we don't care about polynomial increases in time. But coming back to what probabilistic is, so universal Turing machine is deterministic, right? It gives you for every inputs, and you'll get like an output by it'll just deterministically go through the program and give you the output. A probabilistic machine is one where at some states it flips a coin, and then the resulting state of the machine depends on the outcome of that flip. Of course, every universal Turing machine can also simulate the probabilistic Turing machine, because all it has to do is for each branch of the coin flip, if you record all that, it just checks all of those different parts. But you can see that can become rapidly large, right? But in principle, the universal Turing machine can simulate these as well, but this just makes things maybe a little bit, increases the number of sort of operations or efficiency of the system. Okay. And what we think is that quantum computers violate this one. So the strong church Turing thesis, we think, or we have counter examples, we think, that violate the strong church Turing thesis. We believe we have a model of computation called quantum computing, which cannot be simulated by just a classical coin flipping operation at every point. So you should remember this, because later on, when we talk about quantum computers, and I mentioned this, there'll be collapses of the wave function, which will be represented effectively as if the qubit collapsed into state 0 or 1 with some probability. So you might think, oh, I can just represent that by some Turing machine where I just flip a coin at each time to decide whether the computer should be in 0 or 1. But it turns out quantum computers have greater power than that. Okay, so that's sort of good to keep in mind. We are not just saying, oh yeah, this random Turing machine with some randomness thrown in, and somehow you're magically better than regular Turing machines. We think that quantum computers are not just that, they're better than that. Okay. And that class of quantum computers, the complexity class, problems that can be efficiently solved in which is polynomial time, in a quantum computer is given the name BQP, which is something like, I think, bounded error quantum polynomial time. Okay, so BQP, and we have a few examples of algorithms that are in this class. Okay, and that we believe are not in P. Okay, are not in classical, computer time. Okay. So one is factoring, which I've already talked about. This algorithm was is called Shor's algorithm. Then there's two others that have recently been implemented experimentally. The factoring has also been experimented. I think the algorithm came out in 93. The first sort of small demonstration of it was in 95. But that was for very small numbers, right? So it's not really, it didn't really show the power of the algorithm. But at least it shows that you can solve those problems on a quantum computer. And if we could build a quantum computer large enough, we would then beat the performance of classical algorithms. Remember, all the way back in lecture 1 or 2, I showed you sort of the scaling of Shor's algorithm with the size of the RSA 240 RSA encryption scheme, for example. Okay. And these are two other recent ones. These demonstrate or prove these are two problems. One is called random circuit sampling and one is called boson sampling. The way in which these were the problems that these are for is one is to simulate the output of certain random quantum programs, right? If every quantum program could simply be simulated on your laptop by using, Monte Carlo simulations or whatever, then, you wouldn't really need to have a quantum computer to do it, right? But what Google showed in 2019 was that there are, on their computer, there are many, they showed that there are quantum programs, random quantum programs, which would take, I think they claimed it would take thousands of years to solve on even a supercomputer like the Summit supercomputer in Los Alamos, not Los Alamos, Oak Ridge. But that, and then, okay, so the idea was this paper showed what they call quantum computational advantage, okay? And I think they call it supremacy, but I prefer the word advantage, okay? Quantum computational advantage, which is that these are problems in which the quantum computer does way better. They solve this problem on the quantum computer in like a few seconds, versus what they estimate on a supercomputer would take thousands of years. And this is the most powerful supercomputer on the planet right now, right? Which is Summit. And I think there's a new version coming out that's going to be faster, but still wouldn't do the job. I think a few weeks or a couple months later, IBM's claimed that, in fact, they were wrong. They were off in their estimate. If you took the entire storage space of the supercomputer, which we're talking like terabytes, okay? If you could take the entire storage space of the supercomputer and devote it entirely to this one algorithm, then it comes down to a matter of like days, okay? But that would imply like, terabytes of information being processed at the rate that the supercomputer can do it. So basically, nobody can do anything else on that supercomputer for days. And then, yes, you can in fact work it. But all Google has to do is build a quantum processor that's, say, twice as big. And by twice, I think they did this with 54 qubits. So if they built one with like, say, even 60 qubits or something, that's 2 to the power 10, 1,000 times more difficult, okay? So immediately you can see this problem is exponentially scaling, even for the supercomputer. Yes?
So going back to the trick steering thesis,
Yeah.
It's the part that quantum computers violate would be the at most polynomial increase the number of operators or operations.
Yeah, we think.
That's the part we're worried about.
Right. We think that, there's no way to simulate them with just a polynomial increase.
So if there was like a bigger increase in operators, you could still do it on a Turing machine or probabilistic.
Sure. If it goes into super polynomial time, that's exactly what we're looking for. That's the super polynomial speed up of a quantum computer. We can do it on a quantum computer and it'll take, it'll scale much worse on any classical one. That's what we mean. Sometimes you'll hear this called as exponential speed up. Yeah, that's what it's supposed to indicate. Okay, another year or two later, there were two papers on one, which is on boson sampling. It's a very similar problem to the random circuit problem, a random circuit sampling problem. Here, the idea is you send a stream of single photons into a very large interferometer. Remember that interferometer which we were discussing in Wheeler's delayed choice? You send it onto a beam splitter, the beam splitter splits it into two paths, right? And then you recombine it on a second beam splitter. That's like the most basic interferometer. What these groups did in 2020 and 2021, these were in China, they took photons and sent it into an interferometer with hundreds of beam splitters and mirrors. Okay, so the photons, and these are single photons, would take 2 to the 100 paths basically effectively through that interferometer. And now they looked at the outcome of that many detectors, not 2 to the 100, but like about 100 or so detectors. And you can again get a probability distribution of where the photons are detected. This is called bosons sampling because both photons are bosons. Okay, we talked about anyons, fermions, bosons at the very beginning. So because photons are bosons, these boson sampling problems are again, they showed again that a quantum computer, that the classical computers cannot compete with the quantum computation that they did. Okay. Again, these problems are a little bit artificial, right? These two at least, right? The random circuit and the boson sampling. Because after all, in the end, one is you're simulating some random quantum circuit. How useful can that be for real applications? So we don't know. At this point, we don't know. It doesn't seem immediately applicable to a computational problem. But it certainly falls in this larger class of sampling problems, and there are computer scientists who care about things like that. Okay, sampling problems in general. Okay, sampling distributions, etc. And same thing with the boson sampling. It's not surprising that you send a bunch of photons through interferometers, that you can beat a classical computer trying to simulate that process. Okay, because you are actually doing it in physical reality. But that's actually the point of quantum computing, that physical realizations of computers can beat the traditional Turing machine models of computing, which is what all our classical computers realize, right? So that's what basically we're trying to say. And these are, as I said, very primitive quantum computers in some sense. We only have like 50 qubits or 55, or I can't remember the number right now, in the Google one, and now the most recent IBM one has 127, and the boson sampling has now been implemented by people like I think Xanadu or I think Xanadu implemented this on a chip. So now you can start to scale up, say a boson. I mean, it was for boson sampling, but you could imagine doing that with more and more qubits as well. Okay, or for other types of algorithms. Okay, yeah. So that is what I already said, the complexity class. And so this is now we think. Of course, we don't know. Again, there are no proofs in this of all of these claims, but we think the class of BQP is bigger than P, but maybe not as big as NP. But okay, we don't know, right? And maybe there are problems in NP that are in BQP and not in P, but of course, any one of these, I think if you could prove any one of these results, you would sort of be establishing a large class of computational science problems. You'd be solving them if you could do. So, any questions on these things? Okay, so we'll end this sort of section on classical computers by talking about the sort of comparison between classical and quantum computers. And now most of these things will sort of make sense to you. I mean, some of this will not. We'll talk about that in the next section. But so we already sort of covered everything in classical computers here. You know that the unit of classical computation is bits. We have logic gates, but also that could be represented by Turing machines, operations on Turing machines. And the gates, are they reversible? Sometimes, we can construct them if we had to. Universal gate sets exist, like NAND or others that we discussed. And programming languages exist for programming Boolean circuits or digital circuits. We didn't go into it, but your textbook, for example, has examples using Verilog, which is a hardware description language. So it describes, so you can use it to describe like a set of gates and operations, and then the classical, and then the Verilog simulator, but you can also program it into like various circuits, will simulate the operation of that classical circuit. Okay. And then we have an algebra. So we didn't talk about this much, but this allows you to make statements like, if I take A and B and C and I take combinations of A, B, and AB bar and C and so on, can I simplify that set of operations? You could do it, of course, by just constructing the circuit and seeing what it's equivalent to, or seeing what the truth table is equivalent to. But there exists an algebra that allows you to simplify those equations, those sets of constraints. But we didn't again discuss that because that's not the focus of this course. We talked about an error correcting code in a little bit of detail for classical computing, which is a repetition code. And we have talked about the complexity class, which we think all of these problems fall in the complexity class P. And we think that classical computing supports the strong Church-Turing thesis. And then on the quantum side, as we'll discuss, we have the qubit and the equivalent of gates. We call them as unitary gates in the quantum computing side. And are the gates reversible? Always. Quantum computing, it turns out these gates have to be reversed. And there are universal gate sets as well. And we'll discuss all this in some detail, but it's, I'm just giving you the high level overview here. And there's a programming language. In our case, we'll be using the IBM OpenQASM language, okay, to simulate or do some of these quantum algorithms or quantum circuits. And the algebra that allows us to simplify and do the math for these operations is called linear algebra, and we'll introduce that. Error correcting codes exist. For example, the short code is one, and the complexity class is called BQP, and we think that BQP or quantum computers possibly violate the strong Church-Turing thesis. Okay, so that kind of is a comparison. Yes.
Is repetition code not a valid error correction code for quantum as well?
So when we talk about that, we'll see that there are aspects of quantum physics that prevent the direct repetition code from working. Okay, but we can build on the repetition code, and we can use the ideas of quantum physics to make it like a repetition code, but it has to be cleverly done. Okay, so, but the same ideas of like syndromes and all those things will work, but it's just the way we check them has to be different. Okay, and that's what this is called, the Shor code. Okay, I'm going to pause for a second. Any other questions or thoughts, comments? Okay. If not, we will get into our section on quantum computing. So you recall from our quantum physics lectures, we didn't go into how this happens, but we have an interpretation for what's going on in quantum physics, right? Which is that particles do not have a definite location until they're observed. And until then, they're simultaneously in multiple different positions, and this property is called superposition. Okay. And so the waves that we are talking about in this case are so-called probability waves, and we'll make that more sort of concrete in this next section. So as an example, a particle can be in one of two positions, an electron say, can be on, say, on the left atom or the right atom or left quantum dot or right quantum dot in a semiconductor, etc. And all of these properties, like position or momentum or angular momentum, are all probabilistic. Okay. So in quantum computing, what we're going to do is we're going to replace, remember, for a classical computer, we had a 0 or 1, which was the logic for the binary logic for the quantum for the classical computer, to be represented by an open switch or a closed switch. We did some examples of electrical circuits that can simulate, say, a NAND gate or a NOR gate, etc., using switches, right? And a real switch in electronic circuits is done with a CMOS transistor rather than just a mechanical switch. But that's the main. That's only a difference of speed and so on that we have now. We can replace this classical bit by a quantum bit. For example, the electron position that I just showed you on the previous slide, we could label that as 0 or 1. Okay, and I write this 0 or 1 in this special way with this vertical line and this angle bracket. Okay, which is because we call these notation as a ket. Okay, so a ket with something inside it is just a representation of a state. Okay, the state being, for example, that it's on the left or it's on the right. And the quantum state, as we said, has to be written as a superposition of both of these. For the simplest superposition is taking some number alpha, multiplying it by the state plus beta times this state. Okay. So this was originally introduced by Dirac to denote vectors. Okay. And so let's, for example, I already told you left and right, or call it position 1 and position 2. These are two positions of the quantum system that it can have, the electron, atom, etc. And those two positions, we will call them in quantum computer as state 0 or state 1. Okay. So our qubit can be in one of these two positions. So then we say that one position is state 0, ket 0, which is a logical state. So logical state 0 or ket 0 and logical ket 1 is the position 2. So when the electron is in this state or that state, we'll call that logical ket 0 or logical ket 1. Okay. Similarly, for example, you might have the spin of, say, an electron or some other particle, and then the spin up would be logical state 0, logical state 1. Again, ket 0, ket 1. Okay. And similarly, for a photon, for example, the photon could be vertically polarized or horizontally polarized or other states that you could imagine. So those polarizations would again correspond to ket 0 and ket 1. Okay. So those are the logical states for this qubit. And these will all be referred to sometimes as either logical states or computational basis states or just basis state at different times. Okay. So those are all just different words being used for the same idea. Okay. That when the particle is measured, it's always in, say, ket 0 or ket 1. Okay. So now we can introduce what a quantum bit is. Okay. And qubits, which is my preferred spelling with just Q bits, right? Capital Q and then bits. But unfortunately, for whatever reason, the person, I forget the name of the person who introduced this, decided to spell it with the U in between. Okay. So QUBITS, qubits. Okay. And a quantum bit mathematically is defined as a unit vector in a two-dimensional complex vector space. Okay. So that is what a qubit is. And we'll go step by step through each of these ideas that are in this definition. So unit here represents normalized. Okay. So it's equal to normalized. Oh, did I see a hand up? Somebody. Okay. All right. And complex vector space just means vectors with complex coefficients. Okay. You all are familiar with vectors, right? So the vector position of a particle is itself a vector, for example, right? But here we're talking about a vector in an abstract space. This abstract space is called Hilbert space. Okay. And in that Hilbert space, the vectors can have complex coefficients in front of them. Okay. You just think of them as a set of numbers, right? That's what we usually mean when we talk about vectors normally, right? And I take the position of some particle, the lamp or something, I represent that as some XYZ coordinate. That's just a set of 3 numbers. Okay. Now, of course, those numbers have certain important properties. When we rotate the room or when we translate the room, there's a certain way in which those numbers behave. That's what we mean by a vector, right? Or we can have other definitions of vector. The mathematical definition of a vector space is very specific. But in our case, this is an abstract space, which is composed of the 0 and 1 as a basis state. You can think of them as the X and the Y axis for this Hilbert space, right? So if this room, if I had, a position of like 1 square in this room, I would take that corner, I would say, okay, this many units along this axis, that many units along that axis. So those units, those coefficients in front of the vectors in this Hilbert space, the axes are 0 and 1, those logical basis states that I just introduced, 0 and 1. Okay, ket 0, ket 1. Okay. And the coefficients, the number of units in front of those ket 0 and ket 1 are complex numbers. Does that make sense? Because it's very abstract. So, and the general quantum bit, because it can be any vector, right? It could be any square in this room. Over here would be represented by some vector with some coefficients in front of it. That general vector, which is a quantum bit, a qubit, is represented by ket psi. Okay, so ket psi is the qubit, which is represented by this state psi in the two-dimensional Hilbert space. So we can visualize the Hilbert space by this construction, which is called the block sphere. Okay, gives you a nice little way to think about these complex vector spaces. Okay, so the basis state, computational basis state 0, is put at the north pole of this block sphere. The computational basis state 1 is put as the south pole of the block sphere. Okay. And this block sphere has unit radius in this, in this. Now this is three-dimensional, right? So it's x, y, and z. So we went from a two-dimensional complex vector space to something in 3 dimensions, x, y, and z. So you may be wondering, wait, what's going on here, right? But remember, we said there were 2 complex numbers that define the qubit. And as I'll show you, a complex number has two numbers in it, 2 real numbers in it. So there are a total of 4 numbers really in a qubit, right? The 2 coefficients both are complex. So that should be a total of 4 numbers. And then there's a constraint which reduces it down to 3 numbers. So we can represent every qubit as something on the block sphere. Okay, if that's not clear, I'll try to make it clear as we go along. So the block sphere has a unit radius. So you can think of the North Pole or polar bear, right? Okay, polar bears live on the North Pole. They are the zeros. Okay. Anybody know who that polar bear is? Yes.
The wee bear bears.
Yes, yes. Ice bear. Yeah, and then the penguin down at the South Pole. Okay. Happy penguin. All right. So now, how about that quantum superposition that I've been promising? Right? What does that look like? So one of the simplest superpositions I can write is one that has an equal amount of 0 and an equal amount of 1. Okay. But the equal, instead of being half, I write as 1 over square root of it. Why that is, I'll explain when we get a little further down. But just for now, treat it as okay. That's defined. So 1 over square root of 2 times 0 plus 1 over square root of 2 times 1. Okay, the state ket 1. Okay. That is defined or given, and we'll see exactly how that works, to be the x point. This point x here on the block sheet, which is a blue dot over there. Okay. So this state is equal parts of kets 0 and 1. So that would be thought of as the superposition half bear, half penguin, right? Equal parts, bear and penguin. We can also take the negative, right? Because it's just a coefficient in front of that 1, which could be minus sign. Okay. That is formed by a dot on the other side of this x-axis. Okay, this is the x, y, and z. You guys know this, right? X and y, then the z is pointing out. So this is the minus x point, basically, on the block sphere, or minus 0, minus 1, 0, 0 in 3-dimensional coordinates. Again, it's equal parts 0 and 1, but now we have a minus sign. This minus sign represents what we call the phase of the superposition. Okay, so that's all it is. Phase, which turns out to be so important, is just this idea that instead of having a plus sign, I could have a minus sign. Those are the 2 extremes on the block sphere, right? I can go all the way from here to a state over here. Those are 2 different states. Okay. So that's just the penguin inverted over there. Oops, animation went a little wrong. So now the quantum states can also, because it's a complex vector space, that coefficient can have a complex value in front of it. And the one that just has an I in front of it, okay, in front of this one, that gives me a point on the y-axis. So this y-axis is 0 plus I times 1. Okay. And this state also is equal parts of gets 0 and 1. And again, the factor of I is important. I, by the way, is the complex number square root of -1. So this is a complex phase, and that's also obviously important. Okay. That's different from a real -1 and a real +1 in front of I. Okay. So if I want to think about that, that's like a dark penguin, right? The dark side of the force or something. Penguin. Okay. And okay, we can proceed. Now we can put a minus sign in front of that I. That gives me the other side of the y-axis over here. Okay. And in a little bit, we'll come to understand how, if I give you this, I can tell you where you have to be on the block sphere. That's a mathematical transformation that's, that we'll introduce. Okay. So the factor of minus I, again, is important. That's minus square root of -1. That's also a complex phase, and that's different from plus I square root of, which is in front of the previous state. Okay, so we just invert the Dutt penguin. Okay, these 6 basis states that we introduced, or these 6 states, shouldn't say, maybe you can think of them as basis states. I'll explain why later. But I mean, in some sense, you can understand that because the sphere is symmetric, right? I can rotate the sphere and nothing will change, right? I can rotate the sphere by 90, 180, whatever, everything should look the same, right? So in some sense, plus and minus together are like the north and south poles, just with the sphere tilted over by 180, right? Oh, sorry, by 90. Okay. Same thing with this guy, that's just plus and minus tilted again by 90 degrees. Okay. So these are all equivalent north poles and south poles, just along a different direction. Okay. There's nothing that distinguishes, this is not a real globe, right? There are no real penguins or stuff over here. So we could call this side now something else, right? This would be the actual north pole and south. So this is also, in some sense, just as good basis state. That's the difference between a regular computer and classical and a quantum computer, is that all of these basis states, in some sense, are equivalent. Okay, they just correspond to rotations of the blocks. Okay. But we might choose one to be our 0 and 1 because that's what we can easily measure. For example, the position of the electron, or the polarization of the photon, or the spin of some particle, nuclear spin, for example. Okay. But okay, so we'll come back to this. That's our nice penguin and bear combinations that we have. Hopefully this helps you to remember. Oh, what is what? So, oh, sorry, so this plus x, I call it plus x, but in your book, they have chosen to call that plus. Okay. It just means 0 plus 1. Okay. You just remember that. This one is called the minus state, it's 0 minus 1. Okay. The plus I is exactly as it says, which I might call plus y, but that's just plus 0 plus I times 1, and this is 0 minus I times 1. Yes.
So in order to describe the position of the sphere, I would have to give both a complex and a real or give a full x and y.
Yeah, we'll talk about that. Yes.
Would you ever have like a -0 or imaginary 0? Is it always going to be the 1?
What do you mean by that?
Like, would you ever have like 1 minus 0 instead of 0 minus 1?
Oh, that's just the same as 0 minus 1. Well, I'll explain that in okay. No, that's a good point, actually. Because, I mean, I may as well say it since you asked. But if I write 1 minus 0, that's minus outside times 0 minus 1. And it turns out for quantum mechanics, it doesn't care about that minus sign outside the superposition. Okay. That is, the probabilities don't change. Ultimately, we have to care about probabilities. And that doesn't change if there's a minus sign outside the superposition. So if I want to now talk about any point on the block sphere, that's also, a qubit in general is just any point on the block sphere. Remember, I told you a qubit get psi is any linear combination of 0 and 1. So a qubit, this is a qubit. Okay. This qubit state is 0 plus e to the I pi over 6 times 1. Okay. This is also a qubit state, right? I guess I should have said qubit state, but okay. Any of these points on the block sphere is a valid state for the qubit. Does that make sense? So my electron can be in any of these states on the block sphere. I'm restricted only to the surface of the block sphere, by the way. In this, and throughout most of what we do in this course, we'll be only talking about qubits which live on the surface of the block sphere. It turns out going inside the block sphere is also possible, but that just introduces more complications. I probably don't think we'll get into that in this course. Yeah, so I mean, these qubit states were just chosen as, I just chose them as say 0 plus some complex number times 1, and then this is just another complex number, just some random values, and I just plotted them on the block sphere. Okay, and they're all equally good states for the qubit. Okay, any questions so far? So I think I referred to this already. A qubit is specified by 2 complex numbers. Oh, this is just another view. Sometimes I might draw the qubit with the arrow coming out from the origin because it can be hard to spot just the circle. So I might draw it with this arrow just to show you that's where the qubit is. So the qubit is at this point on the block sphere. Okay. So in some sense, we have gained infinitely more information than specifying just 0 and 1, right? Because now we have 2 complex numbers. So, and as we'll see, complex number is made up of 2 real numbers. So we have 4 real numbers now, which describe the qubit, okay, in principle. Turns out 3 is enough, but okay. So that already should tell you we have infinitely more information somehow than specifying just 0 and 1, because 0 and 1 are just 2 states, right? But you may think back to the problem of analog computing that I told you about last week. When we had analog computing, what was one of the problems with analog computing was like, you had these smooth sine waves or whatever in principle, but in practice, as soon as you put that sine wave into an actual electronic circuit, you got all kinds of noise and distortion. So we've reintroduced them back. Okay. So you may think that this is nonsense. Why would I ever want to do that? Okay. So it was, of course, that is one of the reasons people didn't think quantum physics could, or quantum bits would be useful for computing. They were like, oh, I'm just bringing back all the evils of analog computing back. How can this help us? Yeah. So we'll have to get into that. So noise, this is the main reason. Noise, of all types is a problem for quantum computers. So that's why we have to carefully protect our qubits. Anything that causes this qubit superposition to vary destroys my pristine qubit. So you have to be very careful about how you manipulate them, how you measure them, etc., if you want to gain the advantage. That's why it's so hard to get any advantage, unless you are very careful with your physical system to protect this arrow. That arrow can't just be wandering around on the blocks. Okay. So now I'll do a little detour into complex numbers, unless you have questions about anything I've said so far. I know it's still pretty abstract, and that's one of, Yes,
So just going back to the block sphere.
Yeah.
How come it was always the penguin of being inverted turns are?
oh, I don't know. Oh, I just decided that, 0 was our polar bear, right? And so if 0 is the polar bear, and I put a minus sign in front of the 1, which is the penguin, I inverted the penguin. So
Okay.
flip the penguin. Okay. There's no real, thank you though. It's like, I took some thought into it, so I'm glad you asked. Yeah, so even the dark penguin is inverted. So that's a plus I on this side, the minus side, imaginary number on the other side. So it has to be inverted. Okay, so let's talk about complex numbers since we have introduced them for qubits. So what is a complex number? A complex number is defined as z equal to a real number x plus I times a real number y. Okay. So it's a combination of two real numbers, x and y, but with this I thrown in where I is square root of minus 1. Okay. And sometimes, I don't know that you need to know this, but sometimes the geometrical representation of this is called a phasor. Okay. And this polar form is very useful. Okay, so so coming back to this. So we plot the x on something called the real axis, right? That's just our regular axis that we think of all numbers as being along the real line, right? So x is along the real axis, and this I times y, because I is an imaginary number, it means that we have to take y along this axis, which is the imaginary axis. This is not a regular vector space of x and y on this room, like I was talking about. This is an imaginary space, or this is a space of the numbers on the imaginary axis, which have to be always multiplied by I. Okay. So any point in this complex plane, say over here, which is represented by this arrow is the phasor, okay, z. Sometimes you can see a z tilde, it's just a way of specifying this is a complex number, not just a regular real number. Okay. Hopefully, in our case, it'll always be clear from the context. So this complex number z, as you can see, has some angle theta with respect to the x-axis, okay, and has a magnitude. Okay. It all looks very similar to vectors. And many other things are similar to vectors, but there are some key differences. All right. So this z has a polar form, which is also represented here as r and theta, which is just r is just the magnitude of this phasor, because it's not a vector, so that's why I call it a phasor, or the complex number. So this r is the magnitude of the complex number, and the angle of that complex number is this theta. Okay. And if theta increases with time linearly, right, then this phasor will start to rotate clockwise, like this, anti-clockwise. And then if it goes the other direction, that's, it's going negative angles. So that might be, it's rotating clockwise. Okay. But that's for time evolution. We don't have to worry about time evolution for this complex number right now. Okay. Just think about ignoring this part, which is the time stuff. Just think about this over here. Okay. So these 2 points, x plus iy, can be also represented by r and theta. Okay. And this is the complex conjugate of z. Okay. Complex conjugate is just x minus iy. So meaning take the same value of x along the real axis and flip the y-axis. So this is minus 1. And so the phasor looks like the mirror image around the x-axis. So just take this and flip it along the x-axis, and you get the z star, which is the complex conjugate of z. Okay. Again, this is just math. There's nothing special here that I'm talking about. You've all probably seen this at some point. Actually, I'm curious. How many of you have seen some complex numbers? Okay, most of you. Very good. Okay, the real part of z, which is given this notation, fancy script r of z is equal to x, and the imaginary part of z is equal to y, the y-axis, the value the projection, if you like, of the complex number along the imaginary axis is y. The projection of the complex number along the real axis is x. Okay. And x is of course equal to r cosine theta from just this triangle, this right triangle with theta in it, and this side is just r sine theta. And this can all be represented in using the famous Euler formula. We said that r is equal to x is equal to r cosine theta from the geometry, y is equal to r sine theta from the geometry. So we can write z, which is equal to x plus iy, as r times cos theta plus I sine theta. Okay. That is hopefully clear to you from just this geometry here. Z equals x, r cos theta plus I, r sine theta. I take the r out, I get cos theta plus I sine theta. Now, a famous proof, theorem, whatever you like from Euler, showed that this combination cos theta plus I sine theta can be written very simply as just the exponential of I times theta. So that is a famous Euler formula. And so we have z equals r e to the I theta. This makes, for example, multiplication of complex numbers quite easy. Right? If I take two complex numbers and I multiply them, z1 times z2, and one is r1 e to the I theta 1, other is r2 e to the I theta 2, I can multiply the two amplitudes, r1 and r2, and I just add up the angles, theta 1 plus theta 2. Right? Because e to the x times e to the y is e to the x plus y. Okay. So that makes multiplication very simple. And addition is also possible. The rule for addition is very similar to vector addition. Okay. In this complex claim. So yeah, okay, this just talks about the same things I just told you. Complex conjugate z star is x minus iy, which if I go back to this earlier formula, if I put a minus sign here, that's cos theta minus I sin theta. Well, that's just equal to r e to the minus I theta. Okay. Because negative of sine of negative theta is just equal to minus sine theta. So that's how that can be shown. Okay. And the magnitude of z, which is r, right? Which is, or I already told you that the magnitude or this, the length of this vector from the origin. The phasor from the origin. The length of that phasor is r, which is denoted also by the symbol absolute value or norm of z. Okay, and that can be found by taking the square root of z times z star. Okay, and the reason for that is pretty straightforward, which is we'll just do it in a second here. Z equals x plus iy. Z star equals x minus iy. So when I do multiplication of z and z star, this is x plus iy times x minus iy. I expand that out, which is x squared plus iyx and minus iyx, those two terms cancel. Plus, and then I get a minus I squared y squared, right? And I squared is minus 1. So this is the same as x squared plus y squared. Okay. Or another way to say that is z star in the polar form is equal to r times e to the I theta times r times e to the minus I. So that is just r squared. And then e to the I theta times e to the minus I theta, those two will cancel out because e to the x times e to the y is just e to the x plus iy, e to the x plus y. So we get therefore r squared equals x squared plus y squared. And that of course we could also have seen from that phasor. The phasor which was just part of the Pythagoras theorem, we saw that r squared equals x squared plus y squared. But this is useful to remember whenever you get confused and you want to find the norm, the magnitude of a complex number, you now know that all you have to do is just calculate this z times z star. Of course, take the square root, because we found r squared, and so you just have to take the square root to find the norm, the magnitude of z. Okay. Okay, here are some more useful phasor facts. Okay, I already told you about z star. To find the real part of z, all I have to do is take half times z plus z star. So that's the real part of z. This is the last thing I'm going to say. Imaginary part of z is just half z minus z star. Again, something useful if you want to find those real and imaginary parts. Already showed you this one. And then this one is also useful, e to the z. So exponential of any complex number is just e to the x times e to the iy. And e to the iy is just using Euler formula, is cos y plus I sin y. Okay, so I can find that e to the any complex number fairly easily as well. And then the modulus of e to any complex number z is e to the x, where x is the real part, which means that modulo of this e to the iy is always 1. Okay, you can verify this for yourself from the Euler formula, because modulo of e to the iy is just cos squared theta plus sin squared theta, which is always 1. Okay, we're out of time, so I'll do these remaining phasor facts in the next class. Just summarize today's lecture over here.